The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay. I finished up last time talking about lists. And I pointed out that lists are mutable, showed you some examples of mutation. We can look at it here. We looked at append, which added things to lists. We looked at delete, deleting things from a list. You can also assign to a list, or to an element of a list. So IV sub 1, for example, could be assigned minus 15. And that will actually mutate the list. So heretofore, when we wrote assignment, what we always meant was changing the binding of a variable to a different object. Here, we are overloading the notation to say, no, IVs is still bound to the same object, but an element of IVs is bound to a different object. If you think about it, that makes sense, because when we have a list, what a list is a sequence of objects. And what this says is the object named by the expression IVs sub 1 is now bound to the object, if you will, named by the constant minus 15. So we can watch this run here. Idle can't, that's exciting. Hadn't expected that answer. All right, your question.
So say you only have 4 elements in the list of IVs, and you change the 5th element of IVs to negative 15. Will it add an element, or will it give you an error?
Well, I'll tell you how let's answer that the easy way. We'll start up a shell, and we'll try it. All right, we'll just get out of what we were doing here. And so we now have some things. So we, for example, have IVs. I can print IVs. And it's only got 3 elements, but your question probably is just as good for adding the 4th as adding the 5th. So what would happen if we say IVs sub 3, because that, of course, is the 4th element, right? Let's find out. Okay? Because what that does is it's changing the binding of the name, IVs, in this case, sub 1. What it looked at here was the name IV sub 3 and said that name isn't bound, right? That isn't there. So it couldn't do it. So instead, that's what append is for, is to stick things on to the end of the list. But a very good question. So we can see what we did here. And, but of course, I can now, if I choose, say something like IVs sub 1 is assigned minus 15. And now if I print IVs, there it is. And again, this points out something I wanted to I mentioned last time. Lists can be heterogeneous in the sense that the elements can be multiple different types. As you see here, some of the elements are strings and some of the elements are integers. All right, let's look at another example. Let's suppose we'll start with the list. I'll call it L1. This, by the way, is a really bad thing I just did. What's really bad about calling a list L1? Is it L1 or is it 11 or is it LL? It's a bad habit to get into when you write programs. So I never use lowercase l except when I'm spelling a word where it's obvious, because otherwise I get all sorts of crazy things going on. All right, so let's make it the list 1, 2, 3. All right. Now I'll say L2 equals L1. Now I'll print L2, kind of what you'd guessed. But here's the interesting question. If I say L1 is assigned 0, L1 sub 0 is assigned 4, and I'll print L1, that's what you'd expect. But what's going to happen if I print L2? Four, 2, 3 as well. And that's because what happened is I had this model, which we looked at last time, where I had the list L1, which was bound to an object. And then the assignment, L2 gets L1, bound the name L2 to the same object. So when I mutated this object, which I reached through the name L1 to make that 4, since this name was bound to the same object, when I print it, I got 4, 2, 3. So that's a key thing to realize, that what the assignment did was have two separate paths to the same object. So I could get to that object either through this path or through that path. It didn't matter which path I used to modify it. I would see it when I looked at the other. Yes?
How is that different than assigning variables to just a plain where they, like, say you have A equals 2, and then B equals A, and then if you change A to 3, B still equals 2.
So the question is, if I said A is assigned 2, B is assigned A, and then A is assigned 3. That's your question? So the question is, A is assigned 1, B is assigned A is assigned 2, and then if I print B, I'll get 1. Because these are not mutable, this is going to be assigned to an object in the store. So we'll draw the picture over here. That we had initially A is bound to an object with 1 in it. And then B got bound to the same object. But then when I did the assignment, what that did was it broke this connection and now had A assigned to a different object with the number, in this case, 2 in it. Whereas the list assignment you see here did not rebind the object L1. It changed this. Okay? Now, formally, I could have had this pointing off to another object containing 4, but that just seemed excessive, right? But you see the difference? Great question, and a very important thing to understand, and that's why I'm belaboring this point, since this is where people tend to get pretty confused, and this is why mutation is very important to understand. Yeah? I'm just assuming it'll be a great question. Exactly. So very good question. So for example, we can just do it here. The question was, suppose I now type L1 equals the empty list. I can print L1. And I can print L2. Because, again, that's analogous to this example where I just swung the binding of the identifier. So this is important. It's a little bit subtle. But if you don't really understand this deeply, you'll find yourself getting confused a lot. All right? OK, let me move on. And I want to talk about one more type. By the way, if you look at the handout from last time, you'll see that there are some other examples of mutation, including a function that does mutation. That's kind of interesting, but I don't think we need. I think we've probably done enough here that I hope it now makes sense. The one type I want to talk about still is dictionaries. Like lists, dictionaries are mutable. Like lists, they can be heterogeneous. But unlike lists, they're not ordered. The elements in them don't have an order. And furthermore, we have generalized the indexing. So lists and strings, we can only get at elements by numbers, by integers, really. Here, what we use is think of every element of the dictionary as a key value pair. Where the keys are used as the indices. So we can have an example. Let's look at it. So if you look at the function showDix here, you'll see I declare a variable called e to f. Think of that as English to French. And I've defined the dictionary to do translations. And so we see that the string 1 corresponds, the key 1 corresponds to the value 1. The key soccer corresponds to the French word football, etc. It's kind of bizarre, but the French call soccer football. And then I can index in it. So if I print e to f of soccer, it will print the string football. So you can imagine that this is a very powerful mechanism. So let's look what happens when I start to run this. All right. So it says not defined. And why did it say not defined is an interesting question. Let's just make sure we get this right. We'll start the shell up again. All right. So I run it. And sure enough, it shows football. What happens if I go e to f of 0? I get a key error. Because remember, these things are not ordered. There is no 0th element. 0 is not a key of this particular object. Now, I could have made 0 a key. Keys don't have to be strings. But as it happened, I didn't. So let's comment that out so we don't get stuck again. Where we were before. I've printed it here. You might be a little surprised of the order. Why is soccer first? Because the order of this doesn't matter. That's why it's using set braces. So don't worry about that. The next thing I'm doing is, so that's that. And then I'm now going to create another one, N to S for numbers to strings, where my keys are numbers. In this case, the number 1 corresponds to the word 1. And interestingly enough, I'm also going to have the word 1 corresponding to the number 1. I can use anything I want for keys. I can use anything I want for values. And now if we look at this, we see I can get this. All right, so these are extremely valuable. I can do lots of things with these, and you'll see that as we get to future assignments, we'll make heavy use of dictionaries. Yeah, question?
Since they're not ordered, like, can you do a for loop?
You can, but you don't know what order you'll get them in.
Okay.
What you can do is you can iterate keys, which gives you the keys in the dictionary. And then you can choose them, but there's no guarantee in the order in which you get keys. Now, you might wonder, why do we have dictionaries? It would be pretty easy to implement them with lists. Because you could have a list where each element of the list was a key value pair. And if I wanted to find the value corresponding to a key, I could say for E in the list, if the first element of E is the key, then I get the value. Otherwise, I look at the next element in the list. So adding dictionaries, as Professor Grimson said with so many other things, doesn't give you any more computational power. It gives you a lot of expressive convenience. You can write the programs much more cleanly. But most importantly, it's fast. Because if you did what I suggested with the list, the time to look up a key would be linear in the length of the list. You'd have to look at each element until you found the key. Dictionaries are implemented using a magic technique called hashing, which we'll look at a little bit later in the term, which allows us to retrieve keys in constant time. So it doesn't matter how big the dictionary is, you can instantaneously retrieve the value associated with the key. Extremely powerful. Not in the next problem set, but in the problem set after that, we'll be exploiting that facility of dictionaries. All right, any questions about this? If not, I will turn the podium over to Professor Grimson, having stolen a good...
Feels like tag team wrestling, right? Professor Guttag has you on the ropes. I get to finish you off. We are. Here we go. Try this again. Okay. We wanted to finish up that section. We're now going to start on a new section, and I want to try and do 1.5 things in the remaining time. I'm going to introduce one topic that we're going to deal with fairly quickly, and then we're going to tackle a second topic. It's going to start today, and we're going to carry on. So let me tell you the two things I want to do. I want to talk a little bit about how you use the things we've been building in terms of functions to help you structure and organize your code. It's a valuable tool that you want to have as a programmer. And then we're going to turn to the question of efficiency. How do we measure efficiency of algorithms? It's going to be a really important thing that we want to deal with. And we'll start it today. It's undoubtedly going to take us a couple of more lectures to finish it off. Right, so how do you use the idea of functions to organize code? We've been doing it implicitly ever since we introduced functions. I want to make it a little more explicit, and I want to show you a tool for doing that. And I think the easy way to do it is to do it with an example. So let's take a really simple example. I want to compute the length of the hypotenuse of a right triangle. And yeah, I know you know how to do it, but let's think about what might happen if I wanted to do that. And in particular, if I think about that problem, actually I'm going to do this. If I think about that problem, I'm going to write a little piece of pseudocode to think about how I would break that problem up. So pseudocode. Now, you're all linguistic majors. Pseudo means false. This sounds like code that ain't going to run. And that's not the intent of the term. When I say pseudocode, what I mean is I'm going to write a description of the steps, but not in a particular programming language. I want to simply write a description of what I want to do. So if I were to solve this problem, here's the way I would do it. I would say, first thing I want to do is I want to input a value for the base as a float. I need to get the base in. Second thing I want to do, I need to get the height. So I'm going to input a value for the height also as a float, a floating point. Okay, I get the two values in. What do I need to do? Well, you sort of know that, right? I want to then do, I need to find the square root of b squared plus h squared, right? The base plus the height. That's the thing I want for the hypotenuse. And I'm going to save that as a float in height for hypotenuse. And then finally, I need to print something out. Using the value in height. Okay, whoop-de-doo, right? Come on, we know how to do this. But notice what I did. First of all, I've used the notion of modularity. I've listed a sequence of modules, the things that I want to do. Second thing to notice is that little piece of pseudocode is telling me things about values. I need to have a float. I need to have another float here. It's giving me some information. Third thing to notice is there's a flow of control, the order in which these things are going to happen. And the fourth thing to notice is I've used abstraction. I've said nothing about how I'm going to make square root. I'm using it as an abstraction, saying I'm going to have square root from somewhere. Maybe I'll build it myself. Maybe somebody gives it to me as part of a library. So I'm burying the details inside of it. I know this is a simple example, but when you mature as a programmer, one of the first things you should do when you sit down to tackle some problem is write something like this pseudocode. I know Professor Guttag does it all the time. I know for a lot of you it's like, okay, I got a heavy problem. Let's see, DEF, foobar, open paren, a bunch of parameters. Wrong way to start. Start by thinking about what are the sequences. This also, by the way, in some sense gives me the beginnings of my comments for what the structure of my code is going to be. Okay, if we do that, and if you look at the handout then, I can now start implementing this. And I wanted to show you that. So first thing I'm going to do is say, all right, I know I'm going to need square root in here. So I'm going to, in fact, import math. And that's a little different from other import statements. This says I'm going to get the entire math library and bring it in so I can use it. And then what's the first thing I wanted to do? I need to get a value for base as a float. Well, okay, that says I'm going to need to do input of something. And you can see that statement there. It's got the wrong glasses on, but right there I'm going to do an input with a little message, and I'm going to store it in base. But here's where I'm going to practice a little bit of defensive programming. I can't rely on Professor Guttag if I give this code to him. I can't rely on him to type in a float. Actually, I can because he's a smart guy. But in general, I can't rely on the user. Actually, he's right. You know, he would not do it just to see if I'm doing it right. I can't rely on the user. I want to make sure I get a float in it. So how do I do that? Well, here's one nice little trick. First of all, having read in that value. I can check to see, is it of the right type? Now, this is not the nicest way to do it, but it'll work. I can look at the type of the value of base and compare it to the type of an actual float and see, are they the same? Is this a real or a float? If it is, I'm done. How do I go back if it isn't? Well, I'm going to create a little infinite loop. Not normally a good idea. I set up a variable here called input OK. Initially, it's false because I have no input. And then I run a loop in which I read something in. I check to see if it's the right type. If it is, I change that variable to say it's now the correct type, which means the next time through the loop, I'm going to say I'm all set, and I'm going to bounce out. But if it is not, it's going to print out a message here saying, you screwed up, somewhat politely, and it's going to go back around. So it'll just cycle until I get something of the right type. Nice way of doing it. Right, what's the second thing I do? Well, I get the same sort of thing to read in the height. Once I have that, I'm going to take base squared plus height squared, and there's a form that we've just seen once before. I'm just going to repeat it. That is math.squirt, and it says the following. It says, take from the math library the function called squirt. Okay? We're going to come back to this when we get to objects. It's basically picking up that object and just applying that, putting that value into height, and then just printing something out. And again, if I just run this just to show that it's going to do the right thing, it says enter base. I'm obnoxious. It says, oops, wasn't a float, so we'll be nice about it. And I enter a height, and it prints out what I expected. I just concatenated those strings together, by the way, at the end. All right, notice what I did. Okay? I went from this description. It gives me some information. I need to have a particular type. I made sure I had that particular type. I've used some abstraction to suppress some details here. Now, if you look at that list, there's actually something I didn't seem to check, which is I said I wanted a float stored in height. How do I know I've got a float in height? Well, I'm relying on the contract, if you like, that the manufacturer of Square Root put together, which is if I know I'm giving it two floats, which I do because I made sure they're floats, the contract, if you like, of Square Root says I'll give you back a float. So I can guarantee I've got something of the right type. Okay, I know this is boring as whatever, but there's an important point here. Having now used this pseudocode to line things up, I can start putting some additional structure on this. And in particular, I'm sure you're looking at this going, well, look at that if we look at the right piece, going, wait a minute. This chunk of code and this chunk of code, they're really doing the same thing. And this is something I want to use. If I look at those two pieces of computation, I can see a pattern there. It's an obvious pattern of what I'm doing. And in particular, I can then ask the following question, which is what's different between those two pieces of code? And I suggest two things, right? One is, what's the thing I print out when I ask for the input? And the second thing is, what do I print out if I actually don't get the right input in? So the only two differences are right there and there versus here and here. So this is a good place to think about, okay, let me capture that. Let me write a function. In fact, the literal thing I would do is to say, identify the things that change, give each of them a variable name, because I want to refer to them, and then write a function that captures the rest of that computation just with those variable names inside. And in fact, if you look down, and I'm just going to highlight this portion, I'm not going to run it, but if you look down here, that's exactly what that does. I happen to have it commented out, right? What does it do? It says I've got two names of things, the request message and the error message. The body of that function looks exactly like the computation up above, except I'm simply using those in place of the specific message I had before. And then the only other difference is, obviously, it's a function I need to return a value. So when I'm done, I'm going to give the value back out. Right? And that then lets me get to basically this code. Having done that, I simply call base with getFloat. I call height with getFloat. I do the rest of the work. All right, what's the point of doing this? Well, notice again, what have I done? I've captured a module inside of a function. And even though it's a simple little thing here, there's a couple of really nice advantages to this. All right? First one is there's less code to read. It's easier to debug. I don't have as much to deal with. But the more important thing is I've now separated out implementation from functionality, or implementation from use. What does that mean? It means anybody using that little function getFloat, doesn't have to worry about what's inside of it. So for example, I decide I want to change the message I print out. I don't have to change the function. I just pass in a different parameter. If I, sorry, let me say it differently. I don't need to worry about how checking is done. It's handled inside of that function. If I decide there's a better way to get input, and there is, then I can make it to change, but I don't have to change the code that uses the input. So if you like, I've built a separation between the user and the implementer. And that's exactly one of the reasons why I want to have the functions, is I've separated those out. Another way of saying it is anything that uses getFloat doesn't care what the details are inside or shouldn't. And if I change that definition, I don't have to change anything elsewhere in my code. Whereas if I just have the raw code in there, I have to go off and do it. All right, so the things we want you to take away from this are get into the habit of using pseudocode. When you sit down to start a problem, write out what are the steps. I will tell you that a good programmer, at least in my mind, may actually go back and modify the pseudocode as they realize they're missing things, but it's easier to do that when you're looking at a simple set of steps than when you're in the middle of a pile of code. And get into the habit of using it to help you define what is the flow of control, what are the basic modules, what information needs to be passed between those modules in order to make the code work. Okay, that was the short topic. We'll come back to this some more, and you're going to get lots of practice with this. What I want to do is to start talking about a different topic, which is efficiency. And this is going to sound like a weird topic. We're going to see why it's of value in a second. I want to talk about efficiency, and we're going to, or at least I'm going to, at times also refer to this as orders of growth for reasons that you'll see over the next few minutes. Now, efficiency is obviously an important consideration when you're designing code. Although I have to admit, at least for me, I usually want to at least start initially with code that works and then worry about how I might go back and come up with more efficient implementations. I like to have something I can rely on, but it is an important issue. And our goal over the next couple of lectures is basically to give you a sense of this. So we're not going to turn you into an expert on computational efficiency. There are whole courses on that. There's some great courses here on that. It takes some mathematical sophistication. We're going to push that off a little bit. But what we do want to do is to give you some intuition about how to approach questions of efficiency. We want you to have a sense of why some programs complete almost before you're done typing it. Some programs run overnight. Some programs won't stop until I'm old and gray. Some programs won't stop until you're old and gray. And these are really different efficiencies. We want to give you a sense of how do you reason about those different kinds of programs. And part of it is we want you to learn how to have a catalog, if you like, of different classes of algorithms so that when you get a problem, you try and map it into an appropriate class and use the leverage, if you like, of that class of algorithms. Now, it's a quick sidebar. I got to say, I'm sure talking about efficiency to folks like you probably seems really strange. I mean, you grew up in an age when computers are blazingly fast and have tons of memory, so why in the world do you care about efficiency? Some of us were not so lucky, so I'll admit my first computer I programmed was a PDP-6. Only Professor Guttag even knows what PDP stands for. It was made by Digital Equipment Company, which does not exist anymore, is now long gone. It had, I know this is old guy stories, but it had 160K of memory. Yeah, 160K, 160 kilobits of memory. I mean, your flash cards have more than that, right? It had a processor speed of 1 megahertz. It did 1 million operations per second. So let's think about it. This sucker, what's it got in there? That Air Mac, it's got my Air Mac, I don't know about John's, his is probably better. Mine has 1.8 gigahertz speed. It's 1,800 times faster. But the real one that blows me away is it has 2 gig of memory inside of it. That's 12,000 times more memory. Oh, and by the way, the PDP-6, it was in a rack about this tall, from the floor, not from the table. All right, so you didn't grow up in the late 1800s like I did. You don't have to worry about this sort of stuff, right? But a point I'm trying to make is it sounds like computers have gotten so blazingly fast. Why should you worry about it? Let me give you one other anecdote that I can't resist. This is the kind of thing you can use at cocktail parties to impress your friends from Harvard, okay? Imagine I have a little lamp, one of those little gooseneck lamps. I put it on the table here. I put the height about a foot off the table. And if I was really good, I could hit or time it so that when I when I turn this on switch on the lamp at exactly the same time, I'm going to hit a key on my computer and start it running. Okay? In the length of time it takes for the light to get from that bulb to the table, this machine processes 2 operations. Oh, come on, that's amazing. 2 operations. You can do the simple numbers, right? A light travels basically a foot in a nanosecond. Simple rule of thumb. A nanosecond is what, 10 to the minus 9 seconds. This thing does 2 gig worth of operations. A gig is 10 to the 9, so it does 2 operations. And the length of time it takes light to get from 1 foot off the table down to the table. That's amazing. So why in the world do you care about efficiency? Well, the problem is that the problems grow faster than the computers speed up. I'll give you 2 examples. I happen to work in medical imaging. Actually, so does Professor Guttag. In my area of research, it's common for us to want to process about 100 images a second in order to get real-time display. Each image has about 1 million elements in it. I got to process about 0.5 gig of data a second in order to get anything out of it. Second example, maybe one that'll hit a little more home to you. I'm sure you all use Google. I'm sure it's a verb in your vocabulary, right? Google processes 10 billion pages, John? I think 10 billion was the last number I heard. Does that sound about right?
Maybe in order of magnitude more by now.
Maybe more by now, but let's, for sake of argument, 10 billion pages. Imagine you want to search through Google to find a particular page. You want to do it in a second. And you're going to just do it the brute force way, assuming you could even reach all those pages in that time. Well, if you're going to do that, you've got to be able to find what you're looking for in a page in 2 steps, where a step is a comparison or an arithmetic operation. Ain't going to happen, right? I mean, you just can't do it. So again, part of the point here is that things grow, or to rephrase it, interesting things grow at an incredible rate. And as a consequence, brute force methods are typically not going to work. Okay, so that then leads to the question of, well, what should we do about this? And probably the obvious thing you'll think about is, well, come up with a clever algorithm. And I want to disabuse you of that notion. It's a great idea if you can do it. The guy who, I think I'm going to say this right, John, right? Sanjay Gemawat? With the guy who is a graduate of our department, who is the heart and soul behind Google's really fast search, is an incredibly smart guy, and he did come up with a really clever algorithm about how you structure that search in order to make it happen. And he probably made a lot of money along the way. So if you have a great idea, talk to a good patent attorney and get it locked away. But in general, it's hard to come up with the really clever algorithm. What you're much better at doing is saying, how do I take the problem I've got and map it into a class of algorithms about which I know, and use the efficiencies of those to try and figure out how to make it work. So what we want to do is, I guess another way of saying it is, efficiency is really about choice of algorithm. And we want to help you learn how to map a problem into a class of algorithms of some efficiency. That's our goal. Okay, so to do this, we need a little more abstract way of talking about efficiency. And so the question is, how do we think about efficiency? And typically, there's 2 things we want to measure: space and time. Sounds like an astrophysics course, right? Now, space, usually try it again. When we talk about space, what we usually refer to is how much computer memory does it take to complete a computation of a particular size. Right? So, in fact, let me write that down. It's how much memory do I need to complete a computation? And by that, I mean not how much memory do I need to store the size of the input. It's really how much internal memory do I use up as I go through the computation. I've got some internal variables I have to store. What kinds of things do I have to keep track of? You're going to see the arguments about space if you take some of the courses that follow on. And there's, again, some nice courses about that. For this course, we're not going to worry about space that much. What we're really going to focus on is time. Okay? So, we're going to focus here. And the obvious question I could start with is, suppose I ask you, how long does the algorithm implemented by this program take to run? How might I answer that question? Any thoughts? Yeah. Ah, you're jumping ahead of me. Great. The answer was find a mathematical expression depending on the number of inputs, and it's exactly where I want to go. Thank you. I was hoping for a simpler answer, which is just run it. Which is, yeah, I know, it seems like a dumb thing to say, right? One of the things you could imagine is just try it on an input, see how long it takes. You're all cleverer than that, but I want to point out why that's not a great idea. First of all, it depends on which input I picked. Right? Obviously, the algorithm is likely to depend on the size of the input, so this is not a great idea. Second one is it depends on which machine I'm running on. If I'm using a PDP-6, it's going to take a whole lot longer than if I'm using an Air Mac. Right? Third one is it may depend on which version of Python I'm running. It depends on how clever the implementer of Python was. Fourth one is it may depend on which programming language I'm doing it in. So I could do it empirically, but I don't want to do that typically. It's just not a great way to get at it. And so, in fact, what we want is exactly what the young lady said. I'm going to ask the following question, which is, let me write it down. What is the number of basic steps needed as a function of the input size? And that's the question we're going to try and address. If we can do this, this is good because, first of all, it removes any questions about what machine I'm running on. It's talking about fundamentally how hard is this problem. And the second thing is it is going to do it specifically in terms of the input, which is one of the things that I was worried about. Okay, so to do this, we're going to have to do a couple of things. All right, the first one is, what do we mean by input size? And unfortunately, this depends on the problem. It could be what's the size of the integer I pass in as an argument, if that's what I'm passing in. It could be how long is the list if I'm processing a list or a tuple. It could be how many bits are there in something. So that is something where we have to simply be clear about specifying what we're using as input size. And we want to characterize it mathematically as some number, or some variable rather, the length of the list, the size of the integer would be the thing we'd want to do. Second thing we've got to worry about is, what's a basic step? Right? If I bury a whole lot of computation inside of something, I can say, wow, this program runs in one step. Unfortunately, that one step calls the oracle at Delphi and gets an answer back. Right? Maybe not quite what you want. We're typically going to use as basic steps the built-in primitives that a machine comes with. Or another way of saying it is we're going to use as the basic steps those operations that run in constant time. So arithmetic operations, comparisons, memory access. And in fact, one of the things we're going to do here is we're going to assume a particular model called a random access model, which basically says we're going to assume that the length of time it takes me to get to any location in memory is constant. It's not true, by the way, of all programming languages. In fact, Professor Guttag already talked about that. In some languages, lists take a time linear with the length to get to it. So we're assuming we can get to any piece of data, any instruction in constant time. And the second assumption we're going to make is that the basic primitive steps take constant time, the same amount of time to compute. Again, not completely true, but it's a good model. So arithmetic operations, comparisons, things of that sort, we're all going to assume are basically in that particular model. Okay, having done that then, there are three things that we're going to look at. As I said, what we want to do is we want to count the number of basic steps it takes to compute a computation as a function of input size. And the question is, what do we want to count? Well, one possibility is to do best case. Over all possible inputs to this function, what's the fastest it runs? The fewest, or so the minimum, if you like. It's nice, but not particularly helpful. The other obvious one to do would be worst case. Again, over all possible inputs to this function, what's the most number of steps it takes to do the computation? And the third possibility is to do the expected case. The average, if you want to think of it that way. In general, people focus on worst case for a couple of reasons. In some ways, this would be nicer, do expected case. It's going to tell you on average how much you expect to take. But it tends to be hard to compute, because to compute that, you have to know a distribution on inputs. How likely are all the inputs? Are they all equally likely, or are they going to depend on other things? And that may depend on the user, so you tend to get at that. We're, as a consequence, going to focus on worst case. This is handy for a couple of reasons. One, it means there are no surprises. Right? If you run it, you have a sense of the upper bound about how much time it's going to take to do this computation, so you're not going to get surprised by something showing up. The second one is, a lot of the time, the worst case is the one that happens. Professor Gottag used the example of looking in a dictionary for something. Now imagine that dictionary actually has something that's a linear search to go through it, as opposed to the hashing he did. So it's a list, for example. If it's in there, you'll find it perhaps very quickly. If it's not there, you got to go through everything to say it's not there. And so the worst case often is the one that shows up, especially in things like search. So as a consequence, we're going to stick with the worst case analysis. Now, I've got 2 minutes left. I was going to start showing you some examples, but I think rather than doing that, I'm going to stop here, and we'll give you 2 minutes back of time. But I want to just point out to you that we are going to have fun next week, because I'm going to show you what in the world that has to do with efficiency. So with that, we'll see you next time.